Hello everyone. So we are discussing the EDFA. EDFA is a type of optical amplifier, and basically in this optical amplifier, what we do, we add the iridium ion in the core of the optical fiber. So here you can see this is the iridium doped fiber in which where we have added the iridium ion, we have added this iridium ion in the core of the optical fiber, normal optical fiber. And this is the input signal. This is optical in nature. So optical input signal is given to this erbium doped fiber, and this is the pump laser. This provide the energy to this erbium ion for the excitation to the higher energy state and creating population inversion, and then by stimulated emission, photons are emitted, and as a result we are getting the amplified output signal. So this is the basic principle of this EDFA. So what are the different bands where we are using this particular optical amplifier? So basically we are using this EDFA in two bands, C band, L band. C band is a conventional band, and its range is from 1525 nanometer to 1565 nanometer, and in L band we are using 5070 nanometer to 1610 nanometer wavelength range. So these are the two bands where EDFA is used. So basically EDFA provides high gain and low noise, and in this there is a no polarization, or we can say this is polarization independent, and this can amplify the optical signals in the band of 1.55 micrometer to 1.58 micrometer band, that is in C band and L band. So what previously it was necessary to use the repeaters when we are transmitting the optical signal, but with the use of this EDFA, this need is there is no need of converting the optical signal into electrical. Using this EDFA, we directly amplify the optical signal to higher outputs, and this is the all about EDFA. So this is what I have discussed till now. That these are the two basic wavelength where we are using our laser. In this, here you can see this is the pump laser. So what will be the wavelength of this pump laser? So here we using these two 980 nanometer or 1410 nanometer wavelength for the pump laser. So iridium ion is trivalent iridium ion. Basically, this is trivalent, having valency of 3 in outermost orbit. So this particular element is added to the core, and as we add this atom, the this ion, the characteristics is changed, and this is capable to provide the amplified signal. And for the amplification, we need the pump laser. So we have to give the energy, supply the energy to this iridium doped fiber using this pump laser. So for normal operation, we are using these two wavelength, 980 nanometer and 480 nanometer. And as a result, large amount of energy is released, and we get amplified output signal. Here you can see we get the amplified output signal at the output. So how this will happen? So this can be explained by using this diagram, energy level diagram. Here you can see this is the ground state, and here you can see this is the pump band, this is the metastable band. So we have for describing this energy band diagram, basically we can say that there are three levels: pump band, second one is metastable band, and third one is the ground state band. So what is exactly happening in during the amplification process? This can be explained by using this diagram. So first we have seen there is a one pump laser. So in pump laser, I have already discussed that we are using two wavelength, one 980 nanometer and 1400 nanometer wavelength photon. So these photons excite the electrons to the pump band. So basically, when this energy is applied to the iridium EDFA, then what will happen? The ions are excited and reach up to the this pump band. So we are saying this process, what we call this process, pump transition. After supplying energy from pump laser to the EDFA, the electrons excited to the higher energy level, that is pump band, and this is indicated by transition 1. In transition 1, electrons excited from ground state to pump band upon the application of 980 nanometer photon. So electrons stay for few seconds, for some time in this pump band, then they decay to the metastable state. This is the metastable state. So this is shown by transition state 2. So this is non-radiative decay. Again, when we are supplying 1400 nanometer photon, again there is a pump transition of electron from ground state to metastable. This is represented by 3. In first, there is a transition from ground to pump band. In the third transition, there is a excitation of electrons from ground state to metastable band. Again, from here, electron decay to lower state. This is shown by this transition 4. Now next, few electrons decay to the this ground state band. This is spontaneous emission. Electrons occupying this metastable band decay to the lower energy state, ground state or lower energy state, that is the spontaneous emission, that is transition 5. Now few photons absorbed by the electrons in this ground state get excited to this metastable band. This is the stimulated absorption. This is termed as a stimulated absorption, where the photons are absorbed by the electrons of this ground state. Now here, the now electrons excited to ground state to metastable state after stimulated absorption, and then these electrons get back to original ground state or lower energy state, and while doing so emit the photons of having 1550 nanometers wavelength. So this is the basic mechanism that is happening inside the amplifier. So in next class we will discuss about the different parameters, about the different configurations of EDFA, what are the different components used while the configuring EDFA for a optical amplification purpose. Thank you.